So welcome everybody. So today Carlos, Ismael, Marcos and Jesús will be talking about giving us an update about the status of the contribution of the IAC to the Sloan Digital Sky Survey. And I think none of them needs introduction, so please, Carlos, go ahead.
Thanks, Ricardo. Good morning, everyone. So this is the yearly review that we do pretty much at the beginning of the year or mid-year about the Sloan and the activities that have been happening in the last year. We are now in Sloan 4, in the 4th edition. The Sloan Digital Sky Survey started many years ago, but it continues with updated instruments. It's quite alive. Now, in the current phase, which is 2014 to 2020, there are 3 main projects going on at the same time. We're going from studying nearby stars in the galaxy, in Apogee 2, to studying galaxies, spatially resolved spectroscopically with MANGA, and cosmology as well, large-scale structure, baryonic oscillations with EBOS. Well, in addition to these sort of 3 main projects, there is a lot of interdisciplinary work and a lot of other ideas that are not originally in the design of this service. For example, now there has been a lot of work on binarity and planets with Apogee 2 observations. And for example, David has been doing a lot of observations of stars that are part of EBOS. So, you know, it's bear in mind that despite the main subject of these services are, as I mentioned at the beginning, the Milky Way, cosmology, and spatially resolved galaxies, there is a lot of crosstalk between them and different other projects going on at the same time. There is also TDSS, which is time domain spectroscopic observations, and SPIDERS, which is follow-up of Rosita sources using the BOS spectrographs. The Sloan Digital Sky Survey started back in 1998, and the IAC joined, I think it was 2009 or 2010, probably 2010, and then it was Sloan 3. It involves a couple of dozens of institutions. Currently, it's 25 of them. This is the list of the full members where we are, and well, the IAC is the only institution in Spain that is a full member of the collaboration. And as you can see, some of the best institutions for research in astronomy in the world. The survey, the project is committed to publicly release all of the data. So regularly, once every year or every 2 years, everything that has been observed down to typically 1 or 2 years earlier is being publicly released. The budget is about 60 million for this Sloan 4 project, so it's just 6 years. And it's one of the most productive observatories in the world. And this can be quantified, for example, by the number of papers, close to 7,000 papers so far, that collectively have accumulated 250,000 citations. Statistics for the last few years, the number of refereed papers for the IAC as a whole are in the first line in the top table. For 2005, for 2004, for 2014, 15, 2014 and 15, and 2013 through 2015. And the total numbers, and those papers from IAC authors that in the abstract mention explicitly SDSS or Sloan. And then the table below is only for the period 2013 to 2015 and involves citations. So the bottom line here, as we've found in previous years, is that roughly 10% of the papers from the IAC use intensively Sloan data, and about 15% of the citations that the IAC receives come from papers based on Sloan data. A few things to highlight about the collaboration and how it works. There is a lot of opportunities for early career scientists, meaning postdocs, young postdocs, or relatively young researchers in general that are in the 2nd or 3rd postdoc, to do leadership, to take leadership positions. For example, right now we have in Apogee an announcement for the chairs of the science working groups. There are 3 of those, And I think most ended up being taken by very young people, postdocs. There's early career travel grants to attend the collaboration meetings. These are typically pay one person per year. And in the past, I have here a list of those that have been used. Those that I remember have been using those grants. The latest is Sarah Bertrand, who's going to the collaboration meeting next month. When one contributes to the development of infrastructure in the survey, say hardware or software that is used by the entire survey, then after 1 year of effort, you can claim architect status. And that means that you can essentially sign any science paper of the particular sub-survey you've been working on. Of course, you still have to read the papers, provide comments, understand them, but you can really increase your productivity in this collaboration setting quite a lot if you give to the survey. The publication policy is a long document, maybe 2 or 3 pages long, but it can be summarized very simply. Just saying that basically you can work on whatever you want, and you can publish whatever you find with the survey data. There are no rules, and there is no reserved science at all. You simply have to let the collaboration know what you're working on, so that you don't surprise anyone that is doing exactly the same as you. There is a very simple system by which you post projects on a website, an internal wiki. You simply state a title, your collaborations, your collaborators, and the statement, a simple statement saying what you're planning to do or what you're doing. And there is also a 3-week waiting period before submitting a paper to a journal based on the collaboration data, on private data. You need to first 3 weeks in advance post it on the wiki so everyone else in the collaboration has an opportunity to comment on, and architects can read the paper and ask for authorship. Currently, unlike last year, that the survey was still in, Sloan 4 was still in an early stage, and we had only a handful of projects posted. Now we have over 220 projects already on the wiki. It's very simple to look them up. Just get an account on track SDSS.org. This process takes like 1 minute, and then you send an email, and typically within an hour or 2, you get access. And then you can take a look at all of the projects that are going on, who is involved in which, and all of the documentation for the instruments and how to access the data. A quick review of news in the last year or so. DR13 is available now to the collaboration. It's the latest data release, and it's going to be publicly released this summer. And this includes data taking up to July 2015. Every year there is a collaboration meeting. Typically it alternates between the US and somewhere else. Could be in South America, Asia, or Europe. And this year is in Madison, Wisconsin, in June, at the end of June. And if you plan to attend, please remember to register by June 4th. I was for many years the Collaboration Council representative for, this is a very small committee that basically deals with all of the collaboration issues, accepting external collaborations, solving issues of any kind. And I was doing this for many years, but last year Arturo Manchado took over. So if you have any questions about how to deal with the collaboration in general, ask him. And now we have also a new postdoc from Sweden, Henrik, who's over here, who got a grant in Sweden to come and work with us for a year on Apogee. Okay. Well, after this introduction, now we're going survey by survey, just reviewing the recent news and advances. So the first we'll start with EBOS, and I'll pass over the microphone to Marcos.
Thank you. Okay, so hello everybody. So when I gave this talk last year, and I found out it was quite boring. So I have decided to change the way I look at it. So right now, as we're going to have some results by the end of summer, scientific results, I think I'm going to focus on what kind of results we're going to see from cosmological point of view, from this EBOS survey. So, okay, so some amount of technicalities I talked about last year was this kind of thing, like dark time, blah, 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 blah. So the main thing about this is that with EBOS, we're going to fill the gap that we have with quasars. So as we saw in the previous plot, we can see that BOS and EBOS kind of cover the same range, except for that redshift going from 1.1, let's say, to 2. So it's going to fill that gap using quasars. And then you will be thinking, okay, why quasars are so important for cosmologists? Okay, actually they're not very important. Actually, any baryonic matter, it's important for cosmologists. It could be anything, could be quasars, could be, I don't know, any kind of weird matter, let's say unicorns that can fill the universe. So as long as they follow the imprint of baryon acoustic oscillations, and when I say baryon acoustic oscillations, I mean those wiggles or oscillations in density from the very early universe who got imprinted into whatever matter there is now. So the idea is trying to use large-scale structure to see these wiggles and do some cosmological tests on them. So what are the scientific questions that we are really making ourselves? So the solution to these questions is what we are going to try to approach or to solve with this data for the end of summer. So first of all is like, how does the transition from deceleration to acceleration occur? This is very important because when you have like a universe dominated by matter, then it decelerates. It spans but decelerates. And once dark energy comes into play and gets the dominant source of expansion in the universe, then it starts accelerating. So why is it important to know when did it happen and how did it happen? Because it depends on the amount of matter of the universe, the amount of dark energy in the universe, and of course, the properties of that dark energy. So, okay, so then we have, I mean, if with this data, we can rule out different kinds of dark energy. Let's say that dark energy is not constant. Let's say that it changes in time. We can do that kind of tests with this data. So, of course, is it consistent with existing theories? But that's kind of the question, right? So then second, how does the structure grow during this epoch? Okay, because we're having different information at different redshifts, we know how structure is evolving with time. Why is this important? Because it will depend on your theory of gravity you have. So if it's general relativity, then okay, we know it very well, we know what's the predictions. If it's modified gravity, okay, we know what kind of modified gravity we want to test, and we can see that predictions. So it's from a structure from where we are going to find information about, okay, is there any modification to gravity, or is it just general relativity? Well, just, it's quite a complicated theory, but, well, you know. Then, of course, can we detect anomalies on the very large scales in the universe? That actually the largest scales should correspond, or at least should have something in common with the very early universe. So the thing is that this is a question about what we call non-Gaussianity, more or less. So we're trying to find out whether the initial conditions and whether like the biggest structure in the universe follow these Gaussian random initial conditions. So the thing is, the question here is the universe isolated in some way? Like, was the very early universe isolated so that the random initial conditions could be Gaussian? Well, that's the question. It will be very, very interesting to find out that it is not, so that the universe was in contact with something else at the very early stages. So we will know whether there's something else apart from the universe, let's say, that the universe was in contact with. Okay, then can we detect the effects of cosmic neutrinos? Okay, neutrinos in principle are just some massive particles, right? But they're very, very fast. So they don't account for the increase of more and more complicated structures. Actually, they tend to erase structures because they are so fast, they don't fall into the potential wells, given by gravitation. So they don't account, their mass doesn't account, sorry, for this growth of structures. So the thing is that, okay, they have some impact on the way the galaxies populate the universe. So yeah, let's see whether we can pin down what's the mass of those neutrinos. If they have great mass, then there will be no structure or not big structure. If they have very low mass, then okay, we will see kind of like the same structure as if they were photons. And of course, what is the evolution of bright quasars at all luminosities up to redshift 3? This is not actually cosmological, but it's very interesting too to see how quasars evolve. So the first thing we will be measuring, and this is forecasting. Okay, that's why the black dots are the ones corresponding to the EBOS survey. So the thing is that, okay, because it's forecasting, they assumed some lambda CDM and they just put the plot. So important thing is the error bars and the redshift range. So as we can see, the black dots kind of fill the gap we have between some redshifts and give us more information in other redshifts. So, okay, why? I mean, cosmology is mostly about distances. So that's why we spend so much time measuring in the best way possible distances. Okay, of course, that's because geometry is a lot about distances. And it's also because it's very important for people working on galaxies, on faraway galaxies, to know what are the distances. Because once you have the redshift, you want to know how far is your galaxy. So you need to know like angular diameter distance, luminosity distance, and all these kinds of distances that it will be very easy to find out if we have a very accurate model of how the universe evolved. So that's why distances are so important, and this is another 3 kind of distances that we're going to be measuring. So you can please, these plots I'm showing, they're from some papers that you can find out, it's okay. And this is for forecasting, so please go there for references. And okay, so this is about distances again, but are we gonna measure only distances? Okay, it's not only distances are very important, but no way, of course. We will be measuring extra stuff. In this case, what it's plotted in the y-axis is this growth of structure I was talking about. This is a parameter, F sigma 8, that gives you an idea of how the structure grows. And this is what is going to distinguish between modified gravity or general relativity. We can see there different kind of modified gravities. That's the yellow line and the purple one, and the black one is like the standard model of course, I didn't do this plot. It was Kyle Dawson, very funny guy. I saw him just jumping out of a boat in some conference in Greece. Anyway, twice. So the thing is that, yeah, please refer to the paper if you want to understand perfectly well what this plot means. Okay, then we combined this idea of growth of structure with the idea of distances, and then we can, if we assume some dark energy model, we can measure how well does dark energy model fit with our data. So, and this is the kind of results we will be having, or we expect to have. This is a model of dark energy that evolves with time. So the idea is WA is how it evolves with time, and W0 is how the background, let's say, stays. So the idea is that if W0 is -1, then, if W0 is -1 and WA is equal to 0, then that's standard dark energy, like a constant, a dark energy constant. So it's very, very important, very interesting this to check out how the equation of state of dark energy goes. And last but not least, we will be studying neutrinos. Why? Because this is the kind of effect neutrinos have on large-scale structure. This, for those who knows what the power spectrum is, this is how neutrinos affect the power spectrum. For those who doesn't, just to let you know that this is the effect that we expect to see theoretically from an increase on the sum of the neutrino mass. So, and that's kind of it. And the plot on the right, I think I ran out of time, if I'm not. So, but it's very interesting. It's about an extra property we can know by measuring this sum of neutrinos. So if you are interested into this, please let me know, and in the questions I can discuss this plot a little bit longer, but I don't want to extend much more. Oh yeah, the axis, okay, the axis is the power spectrum taking into account neutrino mass minus the power spectrum with neutrino mass equal to 0, normalized to the power spectrum with neutrino mass equal to 0. The canonical one will be the one with the sum of the neutrino masses equal to 0.06, if I'm not completely wrong. Okay, so it will be the upper one. So, okay, and so that's it. So please, I don't know who's next, Ismael or no, okay.
All right, so let's continue on to the next block. This is manga, and I'll try to give you a very quick overview on the main goals of the survey, where we are right now, and ways, very easy ways in fact, for you to explore the data set and get heavily involved in the project. So this is what, okay, so this is not showing up well. There should be a galaxy somewhere underneath this grid. Basically what we're doing is spatially resolving galaxies, and we're getting spectral properties for every point within a field of view in a galaxy. And for that we're using the same spectrograph that Apogee is using, right? So, sorry, the BOSS spectrographs. What we've done, we designed a number of IFUs with different number of fibers, so from 19 to 127, covering a different field of view, and we have all these available in a given plate, so 18 in a given plate. And on top of that we have 9 more with 7 fiber bundles that we put on calibrating stars. And the idea is to observe 10,000 galaxies with these IFUs. How is the sample defined? Very briefly, 2 main samples, a primary sample and a secondary one that differ somehow in redshift here, but also in their spatial coverage. So the primary sample basically will cover up to 1.5 effective radii in the galaxies, and while the secondary sample goes a little beyond that, up to 2.5, at the expense, of course, of worsen the spatial resolution. The idea was to, well, the database is built from the Sloan archive, and the idea is to flatten a flat stellar mass distribution. And this is how the manga fields are located in the sky. And there was an effort of putting them in places where there were other surveys to get some level of complementarity. So, where are we right now? So what you see up here is the status in the first year of operation, up to July 2015. So at that point, we had observed already over 1,300 galaxies, and this is the split between the different samples. So we have a primary, a secondary, and some ancillary and filiary programs there. In terms of progress, are we doing okay or not? Well, the gray line here is expectation of number of plates per time as a function of time. This is the 6 years of the survey, and we are a little bit behind. We are now, the situation is better. So this was mostly due to weather. More than technical, it was mostly due to weather issues. And we've compensated by somehow reducing we've done some numbers, and we felt that we could decrease the exposure times of the exposure time, and that is helping us to catch up with the gray line. All right? More important for you, the situation with the data. There's been a number of releases and different data reduction versions. The current one, the latest one, is MPL4, that was released in October 2015, that basically contains fully reduced cubes in terms of the data reduction for almost 1,400 galaxies. And, well, so this is cut somehow, Carlos. Part of the thing at the bottom is gone. Anyway, I'll tell you. So, and around 500 stars for the Stellar Library program that, as you know, we are heavily involved in. The data analysis has basically analyzed already all these galaxies, and it's available for you stellar kinematics, emission line maps, and kinematics, and stellar population parameters for all these galaxies. And I'll show you how to access them now. Okay, so it avoids you to go into the trouble of getting the cubes down, analyzing this in whichever complicated way, because this data is not easy to deal with. This has all been done for you. Okay? This is just to show you a little bit how we're doing with the stellar library. It's a very quick glimpse. These are gravity, effective temperature, metallicity, effective temperature, and gravity and metallicity. In red, stars that we have already observed in this parameter space. In blue, stars that we expect to observe soon. At least we've drilled holes already in the plates, so plates are ready to go into the telescope. And in gray, that you can hardly see, is the many more that we expect to do. In total, we are aiming at around 4,000, 5,000 stars at the end of the 6-year period. All right? So we're doing more or less okay. There's been some complications because it's not easy to select stars in these fields. There's some restrictions, but we're making good progress on this. Now, what can I, well, this is completely different from what I have presented. Obviously, I didn't put all this red, but it doesn't matter. So, Carlos showed you that there were already over 200 projects in the wiki for the entire collaboration. 88 of them belong to manga, and you can find the list of projects there. People are very active on this. The Chinese community in particular is super active in manga. They're getting a lot of people. There's 5 technical papers about the survey that will contain all the details you need to know about the instrument, the sample definition, and so on. They are already published. A few more to come, but the most important ones are already there. From the prototype data we got more than a year ago, there were 3 papers on different topics, and there's going to be a papers plus with data from the first year, and these are more or less the topics that are being covered. So from scaling relations, some on stellar kinematics, stellar populations, and ion gas properties. All right, let's say 16 or 18 of those that will come out soon. Some of them, in fact, have been submitted. I mean, I'm part of this one, on the first one on dwarf galaxies. This was submitted 2 weeks ago. Okay. Now, so this is all nice, but how can you get into this and get more active? Well, let me introduce you to Marvin, our friend. And in the good Sloan tradition, there's a lot of effort to make all the data products of the survey available to you in the easiest possible way. And there's a lot of people working on Marvin, this system. So let me just give you a few snapshots of what Marvin is and how you can see the data, and hopefully you will get more excited and get access to it. Get onto it. So this is where you get this is where you need to go, to this web address. You'll land into this page, where you can basically enter your plate number ID or some other properties and get access to the data. And you can explore the data in multiple ways. For example, the very basic one is you have a search, you have a page where you can just search based on a number of parameters. This list I put here, these are fluxes, magnitudes, stellar masses, and so on, things that you can get for the NSA photometric catalog. So if you want to filter by some photometric property of a galaxy, you might want to search this way, okay? But again, there are multiple ways of searching, by plate ID, by date, and so on. Once you are happy and you know what you want, you land and you would define a plate, you land in a page like this, where you basically get the footprints, so the images of all the targets in that plate. And that plate, as you can see, contains many galaxies, but in the 7-fiber bundle I fuse, you have stars. This is a plate, in fact, together with apogee. So apogee, whenever they see holes in our plates, they pull fibers. Okay, and sometimes you also put mini I fuse on stars. So you see, these are all the objects in that plate. You click on one of them, you get the basic information from the NSA catalog, so you know the basic properties. And then you see that up here, there's something called DAP QA. So this is where the magic happens. This is where the data has been processed and where you can get access to the data products, okay? And one of the most basic things you can do is get the central spectra. And what you see here is a central spectra of this galaxy. And in red, the different fitting. This is being fitted with Miles models and emission lines and so on. That will be used later to extract the maps. We use here is Miles, and that's why it stops here, so somewhere around 7,400 Armstrongs. But you see, this is more or less the level of quality you should expect. But the spectra is not the only thing you get. You get already radial profiles of many properties, emission lines, for instance. These are the radial profiles of different emission lines. So this is already available to you. And if you're not happy with this because the grid is too coarse and you want all the gory details, you go to the maps. Okay, and the maps, you basically, here you have a number of options. You get the kinematics, signal-to-noise ratios, pixels, emission line equivalent widths or fluxes. And here as an example, I'm just showing you the H-alpha velocity map, velocity dispersion, some level of the quality of the fit in different regions. This is the stellar kinematic maps, stellar dispersion map, and again, some level of quality of the results. So this is there for you to access. It's very, very simple. There's no need to do any complicated analysis. So if as a first step you just want to do exploration of the data set, it's all there. And it's very simple. So please, I encourage you to go there and get your hands dirty and explore the data set. It's a huge data set. 1,300 galaxies might not seem a lot, but considering there is well over 500 spectra in each of them, it's a lot of spectra to analyze and to work with. Now, the level of observations, the rate of observation is so high that we even get peculiar stuff going on. And we actually see the tracks of planes passing in front of the instrument when we are observing. So all these strikes are just planes or satellites passing by in front of the thing. That's how heavily we are observing the sky with Sloan. Okay? So now, just to wrap up, if you want to get more engaged, you have a number of opportunities here. Apart from going to the wiki, get connected into the projects, get involved in those. You can go to Madison and join the general meeting this June. If you just want manga, very specific, you can go to Shanghai, and there'll be a meeting in November. That is a manga meeting and then a specific workshop to work on different issues. And if you like Marvin so much that you want to get into coding and get heavily involved in that visualization aspect, there's many coding weeks in different places of the US in the coming year, so please just get engaged. All right? Thank you.
Of course, in addition to the meetings and in the wiki, you can always talk to us. We're here precisely for that. And now we change instruments, survey and instrument as well. When we leave aside the optical spectrographs from BOSS and MANGA, which are the same but with a different front end, and now we go to Apogee, which uses a dedicated and a very interesting multi-object infrared high-resolution spectrograph to analyze stars in the Milky Way. As the title of the survey indicates, is the second edition of Apogee. The first one was 2011-2014, and in those 3 years of observations with this spectrograph that can handle up to 300 stars at once, we did about 150,000 stellar spectra throughout the Milky Way, mostly red giants, but also a lot of dwarfs. About 20% of the sample are dwarf stars. Now for Apogee 2, there are interesting news. The scope of the project has been enhanced. And another interesting thing is that there is another spectrograph as well. We have just finished building a copy of the original Apogee spectrograph, and the copy is being installed on the DuPont 2.5-meter telescope in Las Campanas in Chile. So with this second instrument, now we will be able to cover the rest of the galaxy, those parts that cannot be accessible from the north, in particular. The central parts of the galaxy, which is one of the most interesting ones to observe in the infrared due to the obscuration by dust. This is a picture on the left here of the DuPont telescope. Oops. This one here. And this is the usual Sloan one. So starting at the end of this year, the ORRA, the Operation Readiness Review, took place yesterday and the day before in Chile. So everything seems to be in order. The observations will begin this fall, and then since this fall until 2020, we will be observing in parallel in the north and the south. I think it's about a third of all of the nights in the DuPont that will be dedicated to Apogee 2 South. The telescope is very similar to the Sloan one, has a field of view also quite large, it's 3 degrees in diameter, and the image quality also is similar, even though it's much older. News. In addition to the copy of the spectrograph being put in the south, there is significant upgrades in the software. For DR13, the new radar release, for example, we have Mark's models that are much better for dealing and allows us to cool the stars and allows us to go much cooler than with the Curus models that we were using before. And here Aníbal and Olga have been actively developing that, and also Ricardo Carrera. And one of the next upgrades that is coming together, mainly the work of Ricardo, is the use, the consideration of the line spread function on the fly. So far we have been using just a convolution of a single spread function, a single PSF for all of the fibers, all wavelengths, but this spectrograph does not produce Gaussian or even constant LSF for all fibers and wavelengths, but they depend on the particular position on the focal plane. So now what we're doing is using libraries that are stored at a much higher resolution, and they are convolved with the appropriate LSF for each fiber and each wavelength. News. There are a whole bunch of postdoctoral positions open. Here at the IAC, there is an Apogee postdoc that you can apply to. I think it's open until the end of this month. There is a second postdoc dedicated to improving the pipeline for 3 years, which is the Apogee ASCAP postdoc. You can apply to that position, for that position until the end of June. There is another mainly science Apogee postdoc at the University of Virginia in the US, also open right now, I think for a month or so. There is another postdoc in Chile at the Universidad Andrés Bello to work on Apogee science as well and to deal with the data from the south in particular. And there are regular and advanced Severo Ochoa, several of them here, some of them the advanced for 5 years, that can be dedicated to Apogee. And there is a meeting dedicated also to Apogee right before the collaboration meeting. This will happen the weekend, June 25 and 26, right before the general meeting, which is 27 to 29th in Madison, the same place, in a hotel. One of the other things that are happening for Apogee 2 that are new is the observation of RR Lyrae all over the galaxy, and in particular in the bulge, to get radial velocities for them and to map the potential well of the Milky Way. Another interesting, exciting, and anticipated science is planets. We are finding, even though Apogee was designed to do stellar spectroscopy, we are finding lots and lots of planets and brown dwarfs. And here are some examples. This is because the spectrograph is cooled down to 80 Kelvin to perform well in the H-band, and it turns out to be extremely stable. So we can routinely do, without any efforts, special efforts, we can routinely do radial velocities to 100 meters per second or 200 meters per second. APOCASC, this is, well, it should be a C at the end instead of a K. This is a collaboration between Apogee and the Kepler mission oscillations team that are observing, doing pulsations in red giants and other stars. So from that, they can infer the properties of the stars in detail, and if you complement that with the chemistry from Apogee, then the modeling is much more refined, and then you can really nail down a lot of these properties. This was quite successful in Apogee 1, continues with tens of thousands of stars being observed in the Kepler fields, and now they are pointing to the Kepler 2 fields, which are more spread all over the sky, getting other different populations. This is an example of measurements of rotational velocities of the planet host in the Kepler fields. And well, of course, this does not end here. 2020 may seem far in the future for you, but in reality, it's not that far if you really want to continue with big projects like this. So the Sloan team and the Sloan collaboration is now have requested for proposals to see what can be done in 2020 and beyond with the Sloan telescopes. And I pass the mic to Ismael.
Thank you. So I will start explaining a bit the difference between the Sloan facilities, or the facilities that Sloan is using, and other facilities. So on the left you have Apache Point Observatory in New Mexico. So in the background you have the Sloan 2.5 meter telescope. That's the main telescope that Sloan has used. And only recently, as Carlos has explained, the DuPont telescope in Chile is being used. So the future of Sloan is in practice also the future of some of these facilities. So it's not clear what would happen to this, particularly to the Sloan telescope, if there is no project for the next years. So at the moment, there is funding, there are projects going on at the Sloan telescope till 2020. But all the time, the collaboration has to think very carefully and well in advance what to do when that particular phase of Sloan finishes. And that's happening now. When we started in Sloan 3, so 6 years ago, the planning for Sloan 4 was already starting. So this planning is needed because in some cases there is new instruments or new facilities for a given instrument like MANGA or Apogee. So they have to build a new spectrograph, new fiber bundles, whatever, in a very short period of time, and they do it. We do it. We are part of it. We do it. In 3-4 years, you have to finish a new instrument. So that's the situation now. What to do after 2020? Do we close the telescope, or do we still use it for something else? Cosmology is moving to the bigger telescopes. So the 2.5 meter probably will not be used for cosmology because most of these participating institutes are also involved in DESI, so cosmology will move to the 4 meter telescope at Kitt Peak with DESI. So in the foreground you have the ARC 3.5 meter. It's not part at the moment of Sloan projects, but in principle could be used in the future for Sloan-related projects. And then on the right you have Las Campanas with relatively smaller investment of observing time at the DuPont telescope, but it's quite likely that maybe in the future the use of Apogee will be larger in these years, in the 2020 to 2026. So how does well, before that, why are so many people interested in these small telescopes, 2.5 meter telescopes? Carlos has already mentioned these numbers. They are impressive. 6,000 papers, 250,000 citations. It means that a lot of people are behind it, working on the data, but not only working, also producing data that other people use. So most of those papers and citations are not by the people that built the instruments and did the survey, but by you, by the community. Every year there's a new release, and then many new users of the data start analyzing the data and publishing interesting results. All this big list of this is the official acknowledgement. We are part of that. So IAC is not in all the papers, but it's in all the acknowledgements of the papers. So let's see how the process of the planning of the future of Sloan works. This started actually last year, asking for white papers, relatively simple documents with ideas about the science, but also ideas about improvement to the modes of operation, to the instruments, whatever. Then a couple of weeks ago, there was a deadline for letter of intents. Who is going to really planning to propose a new survey? And then in the coming couple of months, there will be a deadline for actual proposals. And by the end of the year, decisions will be taken. What will be done with the Sloan telescopes in the next decade? In order to do all this, a committee has been nominated. You have, well, if you are interested in all this, you have there the main Sloan webpage. You go to Future, and you see all these documents. These documents are public because it's, the current collaboration may not be the future collaboration. There will be new people involved. There will be people that are not anymore in the next decade, maybe. So this the procedure is open to the community, whoever is interested. I'm using some of the information in this the documents that you can get from there. The person that is chairing this steering committee for After Sloan 4 is Juna Kohlmeier from Carnegie, and these are the people involved in the process. That's the timeline, also described in that paper that is available, publicly available. René Walterbos is the chair representing the Astrophysical Research Consortium board. There was a call for white papers that I will discuss a little bit next. There's this nomination of a committee to look after this, and the proposal preparation now and until the end of the summer, and then in the fall there will be proposal evaluation and recommendation to the board, to the ARC board, of what could happen after 2020. So the content of the 15 white papers was quite diverse. So there were papers looking at the improvements in the facility, in the infrastructure. For instance, there are ideas to build a huge IFU of 5,000 fibers, compared to manga ones. They're really very impressive instrument. Improvements in the efficiency of the operations, the model, the telescope. Maybe they will go in the direction of building a fiber positioner instead of plugging the fibers as it is done now by hand. There are ideas to build a high-resolution spectrometer to detect and characterize multiple star systems. Time domain spectroscopy is considered one of the most important possible projects for the future. It's already happening now, but it will be even more in the next phase, probably. There are ideas on quasar variability, multiple quasar spectroscopy, reverberation mapping. So do one field with a lot of quasars and observe them a lot of times to see how the proton region varies as a function of the continuum variations and all that. There is also time domain projects involved with apogee. Follow-up of other surveys. If you have something that you're interested to follow up with the Sloan spectrographs, then you could have an idea to continue in the future. Education and public outreach is a very important part of Sloan, and there are also plans to continue that. And as you see here, the last couple of white papers were not on the Sloan telescope, but related with the 3.5 meter telescope. So to have adaptive optics, high resolution spectrometry, Doppler imaging, improve the TOO observations for both telescopes, the 2.5 and the 3.5, etc. I hear very badly. Deeper.
The imager is been removed. It's in a museum. Is there any proposals for imaging?
For imaging, I don't think there is any proposal for imaging, but I should say that these people involved in Sloan, particularly for EBOS, have actually got the time to survey the southern hemisphere and part of the northern hemisphere also with DECAM, for instance, with the 4 meter, with the Tololo DECAM camera. So I don't think there is a niche for wide field imaging with the Sloan telescope, and the site is not very good in terms of seeing, but okay, so the letter of intents concentrated on two particular aspects. One on science, and there's another particular problem with Sloan, that is the future of the archive. At the moment, you have projects that last 6 years, so it's not clear what will happen with the archive after the end of each particular project. Until now, there has been always a new phase, Sloan 1, Sloan 2, Sloan 3, Sloan 4, so somebody took care of the previous archives. But in practice, at the given point there could be a problem that nobody wants to take care of the archive. They don't have the resources to do that. So one of the motivations of this process is also to find a solution for the data management and long-term archiving. So there was a separate call for letter of intent on that. So as I told you, now is a period already of proposal preparation. Immediately before or after the collaboration meeting in Madison, there will be a workshop to write proposals. If you are interested, now is the time to get involved. Get involved in Sloan 4, as we have already mentioned, Jesús, particularly for manga. But if you're also interested in after Sloan 4, Sloan 5 maybe it will be called, it is now the time to get involved. But not only the science. You could get involved. I mean, there are people here from the instrumentation division, for instance, or from other telescopes that could be interested to become involved in the technology. So we have very powerful groups building instruments quite fast, particularly in areas where we are also building instruments, very large IFUs, robotic positioners, optical and infrared spectrographs, etc. There may be synergies also with other projects. For instance, follow-up, something that you're working on. You can follow those sources with the Sloan telescopes or with the Las Campanas one. And also synergies with our facilities. For instance, WIF. What can we do with WIF that cannot be done with Sloan and the other way around? So are there any complementary programs that we could think of for the WIF time? Also for GTC and also for our robotic telescopes. These are just few ideas, but you may probably have many other. And just to finish, questions on general things, ask Arturo. Me, I'm representative in the advisory council, or Carlos, who is the lead scientist. On manga, Jesús. On EBOS, Marcos, Alberto, or myself. On Apogee, Carlos, Aníbal, Olga, Pedro, Ricardo, Sara, Rafael. And that's all for today. Thank you.
Questions? You want to?
Why don't you use manga to observe stars? I think that one fiber would be enough instead of using manga.
Well, you think that, but you need to correct for the differential atmospheric correction, and you cannot do that with a single fiber because the light, because the wavelength range of the spectrograph is so long. Even if you center in the optical your star within your fiber, in the infrared would fall outside. So you're losing that light. By putting 7 fibers, you can track that light loss and model it and get the perfectly calibrated spectrum. And there's plenty of, in addition, there's also plenty of space left in the apogee plates to put our IFUs and to do something useful. And we thought at the time that building a new stellar library would be useful. So that's why.
You know, because if you ensure that you observe the stars that are used later to interpret the galaxy spectra exactly with the same instrumental setup, you know, that consistency gives you better results.
Well, what people do, what we've done in the past, we basically widen our slit to get a very low resolution spectra and use that to flash calibrate our high resolution spectra. It's an option that could be applied, but this is more efficient. And the possibilities for the number of targets here was really substantial. I mean, in Miles, we did 1,000 stars. Here, we could easily go over 5,000. And we're trying to be even more careful than we were in Miles to probe the parameter space uniformly and so on. So there was an opportunity to do better. That's why we took the chance. That's very far in the future. We're not even seeing that right now. I should have the numbers in my head, but I don't. I think it's 7. We can go together and look at the numbers. We're generally faint, because remember that we cannot go too bright because we saturate. We have a fixed integration time, basically set by, well, we set that in fact, but there's a limit on that. So we typically go very faint, but there's a limit on that too. We can look at the numbers and see how cold we go, because I think this is what you're after.
Question for others. We mentioned 9% of PLC publications are based on SDSS data, but even 50% of the citations are based on these papers. So my question is, have you ever measured our so-called safe citation, SDSS bias? Because it could be that a lot of papers could be cited by the SDSS papers.
Right. Right. Yeah. No, I haven't dig that out. I mean, it would require a little bit more effort than the 5 minutes it took me to build these statistics. I mean, on one hand, and the point of these statistics, as we saw in the past, is to highlight the fact that in general, the average Sloan paper, yes, just the raw average, right? It has more citation than the average of the IAC. That's the point. Of course, that could be a little bit masking the fact that the collaboration is very large, and a good fraction of that will be self-citations. Yes, no doubt.
About this, if you look at the statistics of publications of big observatories, whatever, sometimes they don't include Sloan. If any numbers you do, Sloan is quite high up. If you divide by funding, for instance, so 60 million over 6 years is not that much.
If there are no further questions, then we'll stop here. Thanks for coming.